In today's data centers, cooling systems rely heavily on sensors placed at specific locations. These sensors provide point-level temperature data, meaning we only know what is happening at a particular spot at a given time. However, they do not capture the complete thermal picture. More importantly, they cannot predict how temperatures will evolve in the future. This limitation often leads to delayed responses, energy inefficiencies, and potential risks to hardware due to undetected hotspots. Let's explore how this can be solved using Ansys solutions. To overcome these challenges, we propose a digital twin-based approach. This solution integrates three key components: physics-based simulation, AI-driven prediction, real-time sensor data. Simulation helps us understand the physical behavior of the system. AI learns patterns from historical data, and sensors ensure the model stays aligned with real-world conditions. Together, this allows us to move beyond monitoring and start forecasting temperature behavior. We developed a data center prototype designed to replicate real-world operating conditions. The system takes multiple inputs, including heat generation from server blocks, fan operating speeds, and real-time sensor measurements. Using these inputs, CFD simulation generates detailed thermal data, which is then used to train the AI model. During operation, a calibration layer called Moving Horizon Estimation, or MHE, combines real-time sensor data with model predictions. This ensures that the digital twin continuously reflects the actual system state. The final outcome is the ability to predict future temperatures and identify potential hotspots in advance. To build this system, we developed a CFD model of the data center using Ansys Fluent. The model includes heat-generating server blocks and airflow driven by fans operating at different speeds. We simulated multiple operating scenarios with varying heat loads and cooling conditions. This approach allows us to capture a wide range of thermal behaviors within the system. The simulation generates high-quality data, including temperature distribution and airflow patterns over time. This data forms the foundation for training the AI model. In addition, real sensor measurements are incorporated during operation. By combining simulation data with real-world inputs, the model becomes both physically accurate and practically reliable. For prediction, we use a temporal fusion transformer model. This model is designed for time series forecasting and can capture complex relationships between multiple inputs. It considers historical temperature data, heat load variations, fan speeds, and calibrated system states. Based on these inputs, it predicts how temperatures will evolve over time. A critical component of this system is moving horizon estimation. In real-world scenarios, sensor data can be limited and noisy, while simulations often rely on ideal assumptions. MHE bridges this gap. It combines sensor data with the system model to estimate the true current state of the system. In simple terms, it ensures that the digital twin remains accurate, reliable, and continuously updated. With the calibrated system state and AI-driven insights, we can predict future temperature behavior. This includes identifying where and when peak temperatures may occur. Such foresight enables operators to take preventive action before critical conditions arise. This system enables several practical applications like dynamic adjustment of fan speeds for optimal cooling, reduction of unnecessary energy consumption, early detection of anomalies, improved planning and management of data center operations. The benefits are clear: reduced cooling energy consumption, improved system reliability, and extended hardware lifespan. Most importantly, decision-making shifts from reactive to proactive and data-driven. By combining physics, AI, and real-time data, this approach delivers predictions that are not only accurate, but also trustworthy and explainable.